Welcome, I'm Mr. B, and this lesson is on the factor of safety in engineering. If you like my content, please like and subscribe. Let's get into this. You want to ride this roller coaster? Check it out. It's pretty new here, 2023. It looks pretty neat. Almost looks like giant straws holding up all around. Very minimal, which just makes it look sleek and fast, right? You still want to ride a roller coaster like this? Check this out. It's a big crack that occurred. The news story was that this possibly was operating for about 6 days in this condition, which is not a good thing. And now it makes me wonder about all the roller coasters I've been on in my life and if they had some kind of damage, cracks, or other issues going on that weren't really fully visible. But this is obviously visible from the ground. It's large enough and people took photos of it. Wow. Kind of scary, huh? So what is the factor of safety or safety factor? You say tomato, I say tomato. What is a factor of safety and how do I determine it? Better question, are we on a roller coaster right now? Whoa, that's about the best animation I can do here with my PowerPoint. I just thought I'd have a little fun with that. But those are some of the questions that an engineer might think about. So let's look into how to actually determine factor of safety. And what is it? Well, this is from Wikipedia. Essentially, the factor of safety and safety factor are pretty much just interchangeable combination of words, meaning the same thing. They express how much stronger a system is than it needs to be for an intended load. Safety factors are often calculated using detailed analysis because comprehensive testing is impractical on many projects, such as bridges and buildings or that roller coaster. But the structure's ability to carry a load must be determined to reasonable accuracy. Many systems are intentionally built much stronger than needed for normal usage to allow for emergency situations, unexpected loads, misuse, or degradation. Degradation meaning corrosion of materials when things get very old. Now that roller coaster was new, so it couldn't have been degradation. But what if something happen in the transportation of those pieces to the site or when they're being manufactured? What if something happened to them? We're not here to fully talk about that. Instead, we're going to talk about the factor of safety and how to calculate it, and then maybe take a look at an example. So let's move ahead. Where might you use the factor of safety? Well, like I said, bridges, vehicles, a lot of pickup trucks, they put a load capacity on it because they market it and advertise, say, 1 ton, 1.5 ton, stuff like that. Here, obviously, he's overloading it. This is something that happens often. You think, oh, it's just temporary. I need to get this stuff home. But this is extreme, right? He's going to damage that if he even gets out of the parking lot and down the road, and somebody could get seriously hurt. What about though, like some small shelving unit? You might advertise that each shelf can hold 100 pounds. So 1, 2, 3, 4, 5, 6 shelves, that's 600 pounds, maybe more that you might advertise. But do you think people are actually weighing stuff before they put it on the shelf? Or maybe they just pack it on because, hey, I want to roll it around somewhere and get it there. Who knows? Things get misused all the time. And as an engineer, you can't really control that stuff. And there are many other places that factor of safety might be used or considered in your design. How do we do it? How do we determine a factor of safety? Well, we have a couple tables. The first table here is for A, B, and C characteristics to find an N1 value in our safety factor. And you'll see in a bit that's going to be using a formula. But our A value is the quality of materials, workmanship, maintenance, and inspection. The B characteristic is control over applied loads. Now remember, that could come down to the end user. You can't control that all the time. C, accuracy of stress analysis, experimental data, or experience with similar parts. Maybe you're just building this stuff all the time or similar stuff, and you have a really good understanding of it. Our table 2 is going to be our D and our E characteristics to find our N2 value in our formula. So D is danger to people. Can people get hurt? Could death occur? And then if that happens, what's the economic impact? Right? Could it be lawsuits, or is it just going to be replace a broken component or a recall that still costs you money, but not like huge lawsuits like death and injury? All that we're going to put into the Pugsley method for factor safety. Our N1 times our N2 from each of these tables equals our NS. That's our safety factor. Now all this stuff I want to note, I have got this from a class. Dr. Rizza at MSOE presented all of this stuff, and that's where I learned it, and I'm just passing this along for anyone else to try to comprehend, understand, and maybe use in a class or in the workplace. Let's use an example here. One that Dr. Rizza gave, elevator cable. Now in an elevator, you might put a factor of safety on the entire elevator or just components. In this case, we were talking about the cable. But RA, quality of materials, workmanship, maintenance, and inspection. Think about it. Elevators, they've been around many years, like probably over 100 years now. They're all over the world. And when you got people building them, installing them, and the maintenance, and even inspection, all those people are usually, they're technicians or service people that they are certified, they have experience, they know what they're doing. Also, the parts are made by reputable manufacturers, stuff like that, right? So if I were to document my thought process like that, I might put down lives are at stake, so quality materials, workmanship, maintenance, and inspection factors are going to be very good. And that's just because I think they've been around a long time. You make a lot of them, and the whole process is just looking to have a lot of safety into consideration. Now, our second part, B, control over applied loads. Remember earlier I talked about you can't really control the end user, right? Think about some elevators you might have been on in your life, and you want to get somewhere and you see a packed elevator, you try to sneak in there, squeeze in, or you're moving. If you ever had to move anyone in a big building, tall building, and you want to pack it full of stuff because you don't want to make a lot of trips. Think about college students going in a dorm, packing it full, and then there's people packed in there. You're probably overloading that thing, right? It says capacity of 10, and now you have 15 people, and somehow you got a mattress in there, which isn't too heavy, or some other supplies or equipment or something else, or maybe you didn't put people. Lots of equipment, you just pack it full. Send it on up to someone to unload. It could easily be overloaded, right? So in that case, I wrote, it is possible to have overloading of passengers and equipment into the elevator cart. So fair to poor for that scenario. Next one, accuracy of stress analysis, experimental data, or experience with similar parts. Well, as I spoke before in the A, these elevators are built and installed and maintained around the world. So I'm expecting that to be really good. And that's what I wrote. The elevator and parts industry has been operating for many years and very reputable. So very good. So what do we do with this now? All right, we're going to look at our table here. I want you to follow me here somewhat. In our A, we chose very good, right? So that's over here, our A characteristics down the row here. Very good, good, fair, and poor. So in this section coming across, this is going to be a value somewhere in here, but which value do we choose? Let's look at some more choices here. Our B, control over applied loads. We chose fair to poor down these two columns. We still have a lot of numbers we could possibly have here. So let's look at our C, which was very good right there. So we are in the whole section of A, very good. Our B column here, B column there. C, we come across 1.5 to 1.7. Let's choose the higher value, have a little cushion. Take the higher value, 1.7. All right, that's our N1 we're going to use in our formula. Our next table, we have our D and our E. We're going to try to determine characteristics and how to choose out of the table. So danger to people, the elevator. Could people get hurt? Yes. Could death occur? Unfortunately, yes. It could be pretty bad. So we're going to put very serious. The danger to personnel if failure occurs could be death. Very serious. That's VS over here. Economic impact. Well, if there's deaths, there could be lawsuits, could be very expensive. Also, your business name, if you built it or installed it, you may be brought into the public eye. Now you may lose business, go out of business. It could be very serious, right? Economic factor could be very serious if people die and lawsuits occur. So, very serious for both. We have D is very serious. E is very serious. You follow the row down the column, 1.6 becomes our N2 value that we're going to use in our formula. We have the Pugsley method for FOS. Our N1 times N2 equals our NS. That is our safety factor. Plug and chug. You put in the 1.7 times 1.6, you have 2.72. That is our safety factor that we might use for our elevator design and components such as the cable. And that's just subjective, but you could see how he's putting some thought process and reasoning behind my choices as I wrote them out and documented them, right? So what could be some advantages and drawbacks to a factor of safety? Well, like I was just saying, it gives some validity to your design by documenting it. And then it could be used for all the components in one design, or maybe just one of the main components. That's kind of dependent on your design, what your parameters are. But I think the most important is documenting your thought process, so that way a manager, a boss, or if someone down the road needs to get a better picture of why it was designed or why selections of components or materials were made, that it was based off of some kind of real choices that then, like you saw, come into consideration to choosing out of the table and then calculating a realistic factor of safety, and not just spitballing some number like, oh, we should build it 2 times stronger, or nobody's gonna get hurt, right? So we'll just, whatever we have laying around, we'll build out of that. Well, that doesn't make any sense, right? That's when it comes back to bite you. Some drawbacks, kind of subjective, right? And opinions vary between person to person. But that's why you want to validate it through your documentation. And then in the end, unexpected failures and outcomes may still occur. People can overload things in the craziest ways, like you saw that pickup truck earlier, or the roller coaster. They probably designed the thing pretty strong, but something still failed on it, right? And it failed in that one joint, but you could see in the picture further, it didn't fail in the other ones. So there's something going on there. And it's overall pretty hard on the brain, right? So don't overthink it too hard, but put some thought process in, document your choices, so at least if you need to validate it, you have something to back it all up with, right? Now, where do you think the factor of safety may have been on this roller coaster? You could take this opportunity now that you've seen how to kind of play the tables out there and all your constraints in your A, B, C, and D, E values. Maybe I bet you it's around the elevator. But this is a one-off, or a company who's making roller coasters, they maybe make a bunch of roller coasters, but they don't always make the same one, right? So this is very unique. And in this structure, when I look at it, I'm thinking they must have had a minimal floor print. Basically, why didn't they put some bracing coming out, for compression? This is in tension here. Maybe they had limited space and they couldn't, so they designed it this way. And remember how I talked about it looked like straws, like tubes, very sleek. So they were maybe looking for making a roller coaster that was minimalist. But now all that force is on these joints. Now it didn't break back here in this one, but who knows, over time, maybe it was going to break there too. Or this joint just had some weakness, or poor metal, fatigue from some welds going on that probably occurred there, or something else occurred. Maybe when it was shipped to site, some damage occurred that wasn't seen, but somehow it broke. Luckily, it was not a catastrophe and people didn't die, but it just goes to show you that sometimes you can't control everything that occurs. Well, that's factor of safety, explained by me, Mr. B. I hope you like my content. Please like and subscribe. And thank you to Dr. Rizza from my school back in 2015, who presented a lot of this information and taught me well. Thank you very much. I hope you guys have a great day.